In this lecture I will talk about multi-layer feed-forward neural networks, so the first really deep neural networks. We will see the architecture of these networks and define deep neural networks as chained functions. To recapitulate, we started with models formed by a single neuron. We then stacked these neurons to neural networks with a single hidden layer and one output neuron, and then extended the model class to models with several output neurons. We now want to extend the model class once again, such that we allow an arbitrary amount, L, of hidden layers. The general term of this model class is referred to as multi-layer feed-forward neural networks, often only feed-forward neural networks, and feed-forward because the inputs are passed through the network from left to right, and we don't have any backward connections or loops. We can describe such a feed-forward neural network with L hidden layers as a function that is a concatenation of several other functions, as we can see here. Here, the sigma e is the activation function of the E's hidden layer, and phi e is the weighted sum of the inputs of layer E. So we would start with the weighted sum of the inputs here and apply the activation function of the first hidden layer and continue with that. And finally have the weighted sum of the output of the L minus 2 hidden layer, and then to get the activation of the layer L minus 1 by applying the activation function. Finally, we have the weighted sum of the last hidden layer and the activation function of the output layer. So such a neural network is a very nested function made out of a lot of elements, but all these elements are simple. It's just a sequence of in an alternate fashion applying a weighted sum and an activation function. As before, we can collect all the weights associated to one layer to a vector W. We now call it Wi, to denote that it's a weight matrix associated to the E's layer. We have a bias vector BE for the E's layer, and we can calculate activations which are of the hidden layer, of the E's hidden layer, which can be collected in a vector Zi. Of course, if we have L layers, then we have I can be have in the numbers from 1 to L. Now the activation of the E's hidden layer is given by applying the activation function of the E's layer to the weighted sum. That is the product of a weight matrix and the output of layer 1 E minus 1, and at the bias of layer I. When we denote it like that, of course, Z0, so the zero's hidden layer is just the input X. Here again we can note that if we would always apply a linear activation or like identity function in the hidden layers instead of using a nonlinear activation function, everything would boil down to just a model that learns linear decision boundaries. As for a single hidden layer, this can be showed for arbitrary many by just repeating the same argument. The network structure then would look like that. We have a input layer with P inputs. We have then we have L hidden layers, each with their own number of hidden neurons indicated here by M1, for example, for the first hidden layer. For each hidden layer, we have a weight vector, a weight matrix, and a bias vector. Here for the first layer, here for the second, here for the third, and finally for the output layer, we would have a weight matrix again, and a bias vector for the output neurons. The calculations would work as the same as they have worked before, with the only difference that we now apply several layers. So we feed in the input from the left, calculate the input of the first hidden layer, calculate the activation of the first hidden layer, which is here given by the ReLU function, so the max of 0 and the input. So we get the output of the first hidden layer. We can calculate the input of the second hidden layer by multiplying with the weights and adding the bias vector. Calculate the output of the second hidden layer with ReLUs again, and the same for the third hidden layer. And finally, the output of the third hidden layer serves as input to the output layer. And we finally apply a softmax to calculate the final output of the neural network. Now we know that a single hidden layer neural network already has universal approximation property. So why should we add more layers? Intuitively, multiple layers allow for the extraction of more and more abstract representations. As we had an illustrative example in the introduction to this lecture. Each layer can also be seen as adding an own degree of nonlinearity. So one can express more complicated function with a network having more layers than a neural network with just a single hidden layer, and there are theoretical studies on understanding this advantage, as for example this work of Guido Montefa et al., where they quantify the linear regions of ReLU networks. In fact, the deep neural networks, which are implied today, don't have only a few, say 3 hidden layers, but hundreds of hidden layers. So this is really deep, since depth usually refers to the amount of hidden layers used in a network. In the past, when neural networks were invented, such deep neural networks were hard to train. This is because of several reasons. Before, mainly the sigmoid activation function was used, which can slow down the training due to a phenomenon known as vanishing gradients. The introduction of ReLU activation functions helped a lot for this problem. Then, training deep neural networks on CPUs was very slow. Nowadays, neural networks are trained on GPUs, which is orders of magnitudes faster. Then we have much bigger data sets. When the data sets are small, other models, such as support vector machines, may be better than neural networks. Now we usually have very huge data sets, and we have novel architectures that are specifically designed for different data types. This, and together with the faster hardware and better optimization and regularization techniques, makes it feasible to successfully implement and train very, very deep neural networks. Often the increase in depth also translate in an increase in performance, as we can see in several application areas. But it's not just that we apply very deep feedforward neural networks, but really specifically designed network architectures, which are much more complicated than this simple feedforward neural networks, and which we will get to now in the course of this lecture. The term deep learning, the field deep learning, encompasses all of these different developments which are used nowadays when training deep neural networks.